This series of videos is about motion in space. Our learning objectives are to describe the velocity and acceleration vectors of a particle moving in space, and then to explain the tangential and normal components of acceleration. We're not going to cover Kepler's law of planetary motion. However, Kepler's laws of planetary motion is a student presentation that you guys will see pretty soon. Velocity and acceleration for vector value functions behaves very much like velocity and acceleration behaves for normal functions. In BC, you learned that the velocity function is just the derivative of the position function. That is true for vector value functions as well. V of t is equal to r prime of t. And then the acceleration function, a of t, that's just equal to v prime of t, which is also r double prime of t. And then to find speed, all we have to do is take the absolute value of the velocity function. In this case, absolute value just ends up being the magnitude. So speed is the magnitude of the velocity vector value function. Suppose a particle moves in a parabolic path defined by this vector valued function, where t measures the time in seconds. We want to find the velocity, acceleration, and speed as functions of time. And then we want to sketch the curve along with the velocity vector at time t equals 1. Let's start with finding the derivative of r. That would be 2t comma negative 2t divided by 2 times the square root of 5 minus t squared. This fraction will reduce by canceling a 2 in the numerator and the denominator, and that would reduce to negative t divided by the square root of 5 minus t squared. Since we just found the derivative of r, this is actually our velocity vector. Now let's find the speed. This would be the magnitude of v of t. That would be the square root of the x and the y components squared, and then added together. This would give us 4t squared plus t squared, and then if you square the denominator, that radical goes away. We could probably stop there, but it would be good to further simplify this just to see if we can get rid of the radical. I'm going to start by making this 4t squared into a fraction, and then finding a common denominator. So I'll multiply the top and bottom of that fraction by 5 minus t squared. So now we have 4t squared times 5 minus t squared plus t squared. I can write that as a single numerator since we now have a common denominator. This would be 20t squared minus 4t cubed plus t squared, all over 5 minus t squared. Now we would have 21t squared minus 4t cubed, all over 5 minus t squared. Looks like all we could do is factor out a t squared from the numerator. You could take the square root of that t to pull it outside of the radical. So I'm going to call that as my answer for the speed. So now let's find the acceleration vector, which would be the derivative of the velocity vector. That would be 2 for the x component, and then we have to use quotient rule for the y component. Quotient rule gives us all of that. We have a negative sign here and a negative sign there, so those will cancel out. And notice we still have the negative sign out front. That's not going to go away. We have 2 divided by 2, so those will reduce. And so now I'll just split this into 2 different fractions. The first is the negative square root of 5 minus t squared over 5 minus t squared. And then we have a minus sign. And the second fraction would be t squared over 5 minus t squared to the 3/2. Now we can find a common denominator. All I have to do is multiply this left fraction with that square root of 5 minus t squared. That would give us a common denominator, which means that we could write just a single numerator. Squaring that top left radical means that the radical goes away and we're left with negative 5 minus t squared minus t squared all over 5 minus t squared raised to the 3/2. When we distribute this negative, it's going to make the 5 negative and the t squared positive. That means that this positive t squared will then cancel with the negative t squared. So we're left with negative 5 in the numerator, and then the denominator is 5 minus t squared raised to the 3/2. And this is our acceleration vector. So that's part A complete. Now we just have to figure out part B. Sketch the curve along with the velocity vector at time t equals 1. To sketch a vector valued function, apply the method that we used to sketch a parametric equation. We want to plug different values of t into the r of t formula to see what the path of the curve is over a number of different values of t. Let's start with r of 0. This would give us 0 squared, comma 5 minus 0 squared. That would just be 0, comma root 5. Let's try 1. R of 1 would be 1 squared, comma square root of 5 minus 1 squared. That simplifies to 1, comma 2. R of 2. That would be 2 squared, comma the square root of 5 minus 2 squared, which would simplify to 4, comma 1. All right, R of 3. That would be 3 squared, comma the square root of 5 minus 3 squared. 5 minus 3 squared is a negative number, and we can't take the square root of a negative number. Therefore, there is no solution for R of 3. It might be useful to find R for the highest value of t that we can put into this. If we were to input square root of 5 into the R equation, that would give us a 0 inside of that radical. That means we'd have square root of 5 squared, comma square root of 5 minus square root of 5 squared. That would simplify to 5, comma 0. We also need to find the velocity vector at time t equals 1. Here is the velocity vector. I'm just going to erase all the t's and put in 1's where the t's were. This would give us the vector 2, comma negative 1/2. In order to graph r of t, we just want to plot points for the endpoints of each of these vectors in the standard position. Let's start with the vector 0, root 5. We begin this vector at the origin, and we want to go straight up to the square root of 5, which would be somewhere between 2 and 3. That would give us this vector here. For this graph, you don't want to actually plot all these vectors. We only need to plot where the endpoints of each vector is. And the endpoint of this first vector is at 0, square root of 5. Our next vector was 1, comma 2. Starting at the origin, we want to go right 1 and up 2. That would put us at the point 1, comma 2. So the next vector would be at 4, 1, and then the final one would give us the point 5, 0. The way I've drawn this, it looks like it's a straight line, but it really should be more of a curve, like that. Now we need to plot the velocity vector 2, negative 1/2. And we need to plot this at the point for t equals 1. That was this point right here. So on the curve, I'm going to put a dot that represents the point on the graph at time equals 1. And then from there, I'll draw a vector that represents 2, negative 1/2. That would look something like that. That just shows you what direction the particle is headed in at time t equals 1.